All right, let's get right into it. When we talk about homomorphic encryption, a lot of people think of it as this single magical technology, but that's not really how it works. The reality is, well, it's a lot more like a highly specialized toolkit. And like any expert craftsman, the most important thing you can do is know exactly which tool to pull out for which job. That's the first step, and honestly, it's the most critical one.
And this right here, this is the core idea we really need to get our heads around. This isn't just some casual advice. It's the central architectural decision you're going to have to make. Because picking the wrong scheme, it's like trying a hammer and a screw. Sure, you might make it move, but it's going to be ugly, it's going to be slow, and you're probably going to wreck what you're working on. So what are these different tools in our kit? Let's take a look at the three main ones.
First up in the toolbox, we've got BFV. Now, I always think of this one as our precision instrument, like a high-end digital caliper. It's the tool you reach for when there is absolutely zero, and I mean zero, room for error.
And the key word here is exact. BFV is all about working with whole numbers, integers. It gives you a rock-solid guarantee that any calculation you do on the encrypted data will be bit for bit identical to doing it on the raw, unencrypted numbers. 1 plus 1 will always be 2. There's no rounding, no estimating, no close enough. It's perfect fidelity.
So, you might be asking, where is this level of precision an absolute must? Well, think about something like counting votes in a secure election, or maybe calculating account balances in a financial system. In those cases, you can't be sort of right, can you? You need the exact number every single time. For these high-stakes jobs that rely on integers, BFV isn't just a good choice, it's really your only choice.
Okay, so let's put the caliper down and pick up our next tool. This one, CKKS, is built for a totally different kind of work. If BFV is our precision tool, then think of CKKS as our powerful estimation engine. It solves a completely different kind of problem, and that means it comes with a completely different set of trade-offs.
And right here is the core trade-off we're making. With CKKS, we're intentionally giving up that guarantee of perfect precision. It works with real numbers, decimals, and it introduces a tiny and, very importantly, a controllable amount of error into the math. Now, why on earth would you ever want to do that? Simple. Performance. For that tiny bit of precision you sacrifice, you get a massive boost in speed and efficiency, especially for really complex math.
And that leads us straight to its perfect use case, machine learning. Just think about it for a second. ML models are, by their very nature, statistical. They're all about probabilities built on noisy real-world data. A model's prediction is never an exact fact. It's a very educated guess. So in that kind of environment, the tiny approximation error from CKKS is basically just noise in a system that's already full of it. It's insignificant. But the performance gain you get, that's what makes private AI actually possible in the real world.
So we've got our precision instrument, BFV, and our high-speed estimation engine, CKKS. But what if your problem isn't so black and white? What if it doesn't fit neatly into one of those two boxes? Well, that's where our third tool, BGV, comes into the picture. This one is the versatile multi-tool of the bunch.
BGV is really just a fantastic general-purpose scheme. It finds a great balance between the two extremes, offering solid performance for a much wider range of operations than the others. So if you have a workload with a mix of different kinds of math, or maybe you're just not quite sure about the exact constraints yet, BGV is a really robust and flexible place to start.
Okay, so we've laid out the tools on the workbench, we've seen their unique strengths, and just as importantly, we've talked about their built-in trade-offs. So now the big question is, how do we pull this all together and make a smart, defensible decision for our project?
Let's just boil it down. Your decision really comes down to answering a few straightforward questions. Do you need perfect, bit-for-bit integer accuracy, no exceptions? That's BFV. Are you working with statistical data or machine learning where speed with real numbers is everything? That's CKKS. Or do you need a balanced, do-it-all solution for a more general or mixed type of workload? Then you probably want to start with BGV. It always comes back to your specific needs for accuracy, performance, and the kind of data you're working with.
So, you've analyzed your problem, you've weighed the trade-offs, and you've selected the right cryptographic tool for the job. That's a massive step, so congratulations. But as soon as you do that, it brings up the very next and maybe even more practical question. What can you actually build with this thing? What are the real-world limits?
Because let's be clear, picking the scheme, that's just the beginning of the journey. The very next thing we have to do is understand what mathematical operations are even possible inside these encrypted systems. We have to dig into the fundamental building blocks. We're talking addition, multiplication, and see how their behavior changes under encryption. Because that is what truly defines the boundaries of what you can and cannot build.